I gotta get that worksheet. Give me a second, I'm gonna go grab the worksheet.
Alright, let's slide it off. Seriously?
Dude, I woke up at
During
the crack at dawn this morning.
So did I.
What time is that?
Actually, it wasn't early. It was like 6:45. But I like.
Oh.
No. It was.
I woke up at 5.
It was 6
Like
o'clock.
person.
It was 6 o'clock. Shower. I woke up. I was like,
Whoa!
and that sounded.
I don't know.
45 minutes. Huh?
I woke up at 5:25, took a shower, put on my bathrobe, and I was so warm and filled.
Wait, bathrobes are actually a thing?
Yeah.
I wear my bathrobe all the time, I swear.
Well, then.
I used to wear it all the
I'm just
time.
saying.
No, that.
So
I know.
cozy.
I thought, like, my grandma has a bathrobe.
I have a bathrobe.
Mine's red and fuzzy.
Mine's blue.
Mine is
And
black
I had
with
just
white
taken a warm
dots.
shower, and I was so cozy to my bed. I was like, I don't want
Okay,
to.
mine has a giant pocket.
Okay, well, I guess it didn't print. Sweet, so,
Kramer, we really need to move this right here at this angle right here. And then nice desk right there.
This Friday, Saturday.
you like that, wouldn't you?
So I get to see myself leaning like this the whole lesson. Just like this. I love this position.
Don't let me forget to get your worksheet. Okay, quick review. Equilibrium is when what?
Rates are the same. Rates are the same.
Rates of what are the same?
Reactions.
What reactions? Okay. Now there are 3 possible outcomes when you have the rates
Same concentration,
Reaction
products
favored,
higher,
product favored,
reactants
or-
higher.
Okay, product favored reaction, reactant favored reaction, or neither favored, equal concentrations. Okay. What does a K value less than 1 tell you?
That
Yeah.
is
Reverse react.
reactants favored
Reverse or reactant favored. Yep.
Guess what?
because it is products over
There's more that
reactants.
goes into a reaction than just the exo or endo. Okay.
Because it is products over reactants.
Yep. Alright, good. So, what can be a little bit complicated today is we are going to talk about the equilibrium of dissolving. Okay? So when I say equilibrium of dissolving, what is the forward versus the reverse of a dissolving process? What is going to be balanced then? When I know the forward and the reverse will be equal rates, but what is the forward reaction going to be doing?
Dissolving.
Dissolving. What is the reverse reaction doing?
Separating.
Precipitating, or aka undissolving, right? Okay. I think we've talked about this a little bit. When you take and you try to dissolve salt, a certain amount of it will dissolve, but eventually it will what?
Equal out with water.
It will stop, right? You won't. No more salt will dissolve, and that's because you reached what? Equilibrium. Okay, because obviously as stuff starts to dissolve, the ability of more to dissolve is going to start going down. So it's going to start slowing down. The fastest point at which things dissolve is right off the bat, because you have the most space, most possible outcomes for it to dissolve. Okay? When it gets to equilibrium, what's happening is things are dissolving as fast as stuff is coming out of a solution and re-solidifying to produce a solid. Okay? So when we don't see any more change or any more dissolving, does that mean that the forward and the reverse stop reacting? No. It just means they're happening at the same rate.
Why is it that if you like you some salt water that's all dissolved, sitting for a while, the salt will it'll go back to the bottom?
It shouldn't.
Should?
What?
That's what it does. I thought if you like leave this dissolved material in.
What might happen is over time, water will evaporate. And if water evaporates, then you're going to have some solid come out.
Okay.
Right? Because less water you have less than salt that you could dissolve. Does that make sense? So if the water starts to evaporate, less will dissolve and some will precipitate out. But assuming that none of the water evaporated, unless you messed with it, it should stay in solution. Does that make sense?
Yeah. So I guess like if you look at silt, like if you move the silt around in water, it like kind of dissolves in water, but all of a sudden it'll go back to the bottom.
Usually silt doesn't dissolve.
Could just be the
It just it's floating around and then it just settles out on the bottom. Yeah. So that's a different thing. Like if I were to take something that doesn't dissolve and mix it, it might just be floating around in there, and then over time gravity's going to pull it down and it'll sit on the bottom. But if something dissolves, it should stay in solution unless you mess with it somehow. Okay? However, we do know that if I dissolve salt in water and then I boil all the water off, what happens? The salt's left on the bottom. Okay? Alright? So, this is what's going on when you got dissolving process. Okay? When you reach equilibrium, we say that the solution is saturated. You guys remember saturated, unsaturated, and supersaturated? Okay, saturated is the most amount of solute that you can dissolve. Unsaturated means I haven't dissolved as much as I can. And supersaturated is under certain conditions, I can actually get more than the normal amount. Do you guys remember the conditions that are needed to get a supersaturated solution?
High
Okay, increase the temperature, allows it to dissolve a little bit more, and then slowly cool it. I mean that's a little bit different. Alright, so, and it does say up here that the two processes that are reaching equilibrium are the dissolving process and the, like Marty said, the precipitating process. So, solid's producing your ions, but your ions are going back to produce your solid equally as fast, and so you don't notice any change. Okay, so if I were doing the equilibrium expression, what's wrong with that? Something's wrong up there. Solid.
There.
Okay, Morgan said it first, the solid shouldn't be there. Because you cannot change the concentration of a solid. Okay, it goes bye-bye. So it looks like this. And so instead of saying KEQ, they give it a different name. Case. Okay, it's KSP.
Whoa.
What the S and P represent, the S
Solid.
Solubility product. How are you so smart? I read it off.
honestly, that's a really smart thing to do, because a lot of times I'll ask questions and the answer will be on the board and everybody will look at me like they have no idea what I'm talking about. So, it actually is smart to read. Good job, Natalie.
I just don't know where we're at.
Okay? So, solubility product. Where this comes from is, when you're dissolving something, you're usually dissolving a solid or a liquid. Yes, you can dissolve a gas, but what we're going to focus on at this level is typically dissolving a salt. Okay? And salts usually are in what phase, typically? Solid. Okay? So if you're dissolving any salt, you're starting with a solid and you're going to aqueous ions. So in every situation where you're dissolving a salt, you are going to have nothing on the bottom. So the constant when you're dissolving a salt is just the product of your ions. Solubility product. Okay? How many ions? That's referring to its solubility, right? Okay? And your ions are your product. That's why it's called the solubility product. And it'll always be over 1, so you can just remove the 1. Okay? So, if I were to do equilibrium expressions for dissolving a solid, you're still going to do products over reactants. Everything's going to be the same. It's just we're going to call it KSP instead of KEQ.
Do we get dog points if we do that on the test?
If you what?
Do the 101?
Yeah. Huh.
Good night. Does it mean the same thing now?
They mean equilibrium, but one specifically the equilibrium of dissolving versus equilibrium of everything else. Okay? This should make sense. Didn't we say that when you have a K value greater than 1, what did that tell you? Product favor. Well, what's the products of a dissolving process.
More dissolved.
More dissolved, right? More ions in solution. Right? If I have this equation, right? This is our solid. These are our aqueous ions. Does that make sense? Okay, if I were to do the KSP expression of this, it would just be this, correct? Good.
Yeah.
If more of these dissolve, that would mean I would have a higher concentration of this, making the K value do what? Go up. So, the greater solubility, or the more something dissolves, the higher the K value will be. And the more concentrated you will have your ions in solution. Okay? The lower the K value, that means I don't have as much of this, and if I don't have as much of this, that tells us I probably have more of this, right? Okay? So you have less dissolved when you have a lower K value. Okay? Okay. Trying to remember what this is for. Okay, I'm guessing that is going to be product favored or reactant favored?
I'm gonna guess
Products.
product.
Product favored, which means that you have a lot of ions in solution. What would be true about the K value then?
It's
It would be higher. And in this situation,
Wow, this is.
Where-
looks like we got reactant favor. So this is more soluble because my solid dissolved into ions, more ions. This is less soluble because my solid remained a solid and only a few ions dissolved. So more soluble, less soluble. This will have a higher KSP value. This will have a lower KSP value. What do you say?
Stare me down like you're
Okay, so this is just showing this. Okay, so there's no greater than 1 or less than 1 in this case here. Just the higher the K value. The reason why I say there's no greater than or less than is there's no, the solid will never be in the equation, right? Okay. This is something that we have to make sure we understand. I needed to define what I mean when I say, ouch, solubilities. Okay, it says the KSP value, which is the constant, right? I can determine the KSP value if I know the solubility. The question is, what is solubility?
Oh, no way.
Okay? This is, I don't expect you to know the answer to this. I want to make sure you understand what solubility is. So I want you to write or make a note somewhere that when I'm talking about the solubility, I'm talking about the concentrations in molarity. What they're saying is, I don't know.
Oh, yeah.
What they're saying is, okay, this is my KSP expression here. If I know the solubilities of my ions, can I plug them in and find my KSP?
like the solubilization of it. Like ability means like able to, right?
Okay. The ability to dissolve, that makes sense.
But you're not talking about that.
If I know its ability to dissolve, could I find the KSP?
Yeah.
If I know these numbers, can I solve for this number?
Yeah.
Right? Okay? Then it says, if I know the KSP, I can determine the solubility. So I can figure out how much ions are dissolved, which is what we're going to do mathematically. It's a little bit more difficult finding this than finding this. Okay? And I'll explain why here. But let me also explain one other really important thing. This is one thing that I think gets missed a lot. Okay? Knowing ratios of ions. So, let's say I have this for a solid. Finish the equation. Go. Write it down somewhere, I don't care. Somewhere. I just want to see if you guys can remember how to do this. This is breaking down into ions. Finish the equation. Give it a try. If you get it wrong, it's fine. I'm going to show you how this works. We've done this before, but I just want to make sure that you can still do it. Dan, are you with us? Okay, you might want that down. It's probably pretty helpful. Finish the equation. We did complete ionic equations a while ago. You remember that, where we broke all these guys up into their ions? So we have done this before. That gives us an attempt. I need to come around and check.
No.
So I don't know. I want the not the expression. I want the equation. The balanced chemical equation. I'll just
You don't want this?
What's this?
This what you do? I don't know.
Well,
This what you do?
all right. Let's do this. Okay.
Kind of, yeah, it's like brackets.
I've got an aluminum ion, right? What's the charge of that aluminum ion?
3 plus
Okay. How many aluminums do I have?
1.
One. So that one's good. Aqueous. Plus.
2Cl.
Okay. I've got Cl. What's its charge?
It's 1 plus.
1 minus. And how many of them do I have? 3. When you're doing ions, they go as coefficients because they're individual ions. They are not reacted together. Does that make sense, everybody? Okay? Now, what? I need to put aqueous. Quick way to remember, there's a couple ways to remember charge. You could look at the periodic table, look at their oxidation numbers, or you could uncrisscross the subscripts. 3 plus, 1 minus. Okay, you remember writing ionic equation in the crisscross method? Okay, remember that you can uncrisscross them to find the charge, and then it's not going to be together. So this is all completely together. This is where it's broken up into their individual ions.
Are you done there?
Yeah.
Didn't Cl
1 minus.
Diatomic?
7 on 7, yeah.
Yeah, but it's in solution. It's not. Yeah, different when it's in solution. Good. Okay. Now, one thing that I want to make sure that I make very clear here is, if I had 2 particles of this, how many particles of this will I have?
2.
2. How many particles of this will I have? Say that again? 6. This is an important concept to understand. It's not super hard, but let me show you what I mean. If I know the solubility or concentration of this, let's say it's a 5 molar concentration of that. If this goes to completion, what would be the concentration of this?
5 moles.
5 molar. Because it's a 1-to-1 ratio. Everybody see it? Okay? If I have a 5 molar of this, when it breaks up into its ions, what is the concentration of this if it goes to completion? 15 molar. 1 to 3. So when one of these breaks up, I will get 3 of these. So if I have 5 moles per liter of this, I should get 15 moles per liter of this particular ion. This is really, really, really important for the math we're going to do here in a sec. Okay? The coefficients tell you the ratio. Yes, is this a bigger particle? Absolutely. Okay? But this breaks up into 3 times as many smaller particles. Okay? I've got 1 sandwich. That doesn't mean that I have 1 piece of meat, 1 piece of cheese, and you name it. Right? It depends on the recipe. So. I'm trying to remember what this problem is asking. I don't think you do. Quick here. I'm gonna check my thing.
I've eaten this much
Okay,
of a burrito
I'm
once.
just saying.
Okay, so I don't think you have this in your homework or in your notes, so just pay attention here. You guys probably don't remember what barium sulfate is.
It's
Oh, I remember.
BaSO4.
Okay, so I'm going to write the equation. Barium has an oxidation number of 2+, so it's Ba2+, which means that sulfate has to be what? 2 minus. Because I have one of each. Remember, no parentheses.
No.
So one polyatomic ion. Okay? So it doesn't tell you what I'm solving for, so I'm just going to tell you right now. It gave us the solubility. Here it is. And I said, if you know the solubility, you can solve for what? KSP. Right? So here's what you are going to do. In order to find the KSP, I need to write the KSP expression. Okay, this is going to be my solid that I'm dissolving, and these are in ion form, so they are aqueous. Following
There's
everybody.
always going to be a solid if you dissolve it.
Yes, in this class, yes.
He's lying to us.
Okay? Products over reactants, this is a solid, so it's not in, so the equation or the equilibrium expression will just be like this. I have no coefficients, so I have no exponents, correct?
Amen.
Okay, now, remember how I said that if I know the concentration of this, I can figure out the concentrations of this based on the ratio? Okay? Now, I do not, oh, okay, yes I do. I do know the concentration of this. So what I'm going to do is I'm going to represent the ratios of all of these with variable S. S referring to solubility. So since everything is a 1-to-1 ratio, they all have equivalent solubilities. If this is 2 molar, then this is 2 molar. And this is 2 molar. If this is 25 molar, then these are. Because they're all what? 1-to-1 ratios. Now notice, they gave us the solubility, or S, of barium sulfate. So, the solubility of this is 1.1 times 10 to the negative 5 molar, which means these two are also 1.1 times 10 to the negative 5 molar. Okay? But what I'm going to do here is I'm going to simplify stuff so it will hopefully make it a little less work for you. Okay, what do these brackets mean?
Concentration.
Molar solubility,
Oh, shoot.
right?
Yeah.
Concentration and solubility are the same here, right?
1.1 times 10
Okay?
negative 5.
So we could take this and plug it in, but let's just quickly say, what did I say I represented as the solubility here? Just S, right? So I'm going to go KSP equals S times S. Right? Doesn't this and this, aren't they the same? Brackets mean concentration, and solubility is that concentration in molarity. So, in this particular situation, your KSP is S squared. Well, what's S?
1 times 10 to the negative.
Plug it in and solve.
I wouldn't do it like that.
Okay, Gage.
You're right. This one probably is pretty easy, but when we start getting different,
Just plug it in.
if that's how you want to do it, that's fine. But when we start getting different ratios, this way is actually a little bit easier. Okay, if it's just a 1-to-1 ratio, then square it, you're done. If it's not a 1-to-1 ratio, you can't just square it and you're done.
Yeah, so might as well just plug it in.
Okay, you can decide on what you want to do. Right? So, can somebody take 1.1 times 10 to the negative 5th and square?
That is good.
Where's my calculator?
Yep.
0.5.
1 point.
No, but I did have one that was left here. I just don't know where it went. Is that your notepad behind you?
Yes.
There was one that was left here, but I don't know where it went.
I have all of them.
I don't have one off the top of my head right now. Okay, what did you guys get? 1.21 times 10 to the negative 10.
It's going to be 1.21 times 10 to the negative.
Right?
Thanks, just said it 3 times. Oh. Awkward.
Okay, let's do this one. This one's a little bit more difficult. Because the ratio is not what?
1 to 1 to 1.
Okay, we're probably gonna finish with this one, or well, depends. We'll see how far we get. We're probably not gonna finish the lesson today, so we'll probably finish it tomorrow. Which means that your quiz is gonna get pushed back to Wednesday.
That also means that.
Test might be Tuesday then next week. It depends.
Church night.
Okay, it depends.
Church day.
All right.
Okay.
So, but please focus here, because you gotta figure out what it is that they're asking you to solve for. Okay. What did they give you in this problem?
The
KSP. If they give you KSP, they usually want you to solve for the solubility. Okay? If they give you the solubility, you're usually solving for the KSP. That's where I had you made that note where it said if you know KSP, you can find the solubility. And if you know the solubility, you can find the KSP. And this is where knowing the way I'm showing you is going to be more helpful.
That's true.
Okay? So, whenever you're doing these types of problems, the very first thing you should do is write the KSP expression. Okay, products over reactants. This is a solid, so the reactants are going to be 1. Okay? Help me out writing the KSP expression for this, somebody.
CD 2 plus to the third.
Everybody see what happened there? Right there.
And then
The
PO
third.
for.
What? What? I missed the
The
bell.
very front. The very front. You misspelled it.
Try whispering it now.
Nice.
How do you? Why are you getting there?
Oh, right there.
Why are you focusing so intently there?
PO 43 minus.
Why did you have to say that? Oh, sorry.
Why did you notice it?
So now, not every class is going to say that.
Did anybody else see that?
No.
I noticed it was a bit
Why
off.
are you staring at this region?
I noticed it was this.
When you started to write,
I
oh,
saw
the
it.
truth's coming out.
Okay, alright. So, there's my KSP expression.
Time to come out.
Okay? Now, what I recommend doing is representing the solubility with variable S based on the ratios of my reactants and my products. Okay? How many do I have here?
9.
1.
Coefficient?
1.
1. Okay? So the ratio is 1 to 3 to 2, right? So I'm going to represent this as S, because it's 1. Right? This is going to be represented as 3S.
Yes.
And this is going to be represented as
2S.
And remember, we said the S represented the concentration in molarity. And doesn't this also represent the concentration in molarity? So what I'm going to do is I'm going to plop this in. They equal each other. So it will look like this. 3S to the third. 2S to the second. Now we need to simplify. I know you guys really struggle with doing things to the power of. 2 to the third power is what? I'm just asking.
Oh, 8. Oh.
Okay.
I was like, wait, what?
Now, when you have these powers here, they need to be distributed to both things, 3 and S.
9S.
No! No!
Wait, no, 27.
No.
27.
27S to the third. That's simplifying this. 3 to the third power is 3 times 3 times 3. Yes?
Right, yes.
Everyone.
Yes.
And
So
then
3 times
4
3 is 9.
Yeah.
And 9 times 3 is
27.
27.
And then 4S.
It has to be distributed to both. Okay? Let's now simplify this. 2 gets distributed to both. 2 squared is
4.
S to the.
Second. Square.
Now let's simplify further. What's 27 times 4?
Good night.
Hold on.
Wait,
I got the 10 up.
wait,
I got the 10 up.
Oh, never mind.
108.
To the fifth.
We know KSP, right?
Right?
Can we solve for S?
Yes, just divide,
Right, what's
No.
and then square root.
Actually, we fit through. Wait,
I'll get rid of that.
Alright, fine. Good night.
Okay, would it be real hard to plug in this situation?
No, it wouldn't.
Yeah, it would, because you don't know any of the
Okay, well,
concentration.
yeah, but the other way,
Okay.
I thought it would be confusing for other people because it's not always going to be S squared.
Sure. Okay? So, what's the KSP? What they give us? They told us.
The answer on the board, 30.2.
Negative 44.
Equals 108 S to the fifth. Let's solve for S. Divide by? Then, I do not want that 5 there. Depending upon your calculator, there are 2 ways to do this. What do I do if it were squared?
Oh, where's the root?
You do square root. If it's to the 5th power, you do the
Fifth row.
5th root.
How do you do
Here's
that?
another way to do the 5th root. If you do not have the 5th root function in your calculator.
It's the X square root on the left side.
It's to the 1/5 power. Another way to do square root is taking the number to the 1/2 power.
That's right.
I don't know if you guys remember that. So, if you do not have a 5th square root, which a lot of the advanced calculators, I think you can do it. But if you do not have the 5th square root, you can still do it. It's just the power, it's the inverse of it. Okay?
Math 5.
So, I would suggest all of you trying to figure out what your calculator needs to do here right now.
Math 5.
Okay? Did you figure out how to do it? Did you do
I
it?
got it.
Okay. If you have this calculator, you can do the 5th root. Okay, was it in the math function?
Math 5.
Okay? Was it in the math function?
It's right in the front. It's not.
So, I want you to try to figure out if you can do this, because are you going to potentially see this? It's possible. So let's see if you got the right answer. Did you guys get this for your solubility?
Yeah! Woo!
Okay? Which is the concentration of this, when it dissolves, is 7.7 times 10 to the negative 10 moles per liter.
This guy.
Yeah, I think so.
Oh, wait, you're getting this.
Find it?
He has homework! No.
We'll finish this lesson tomorrow.
Do you want some Mountain Frost?
Yeah.
What's the mountain? I know.
Mountain Frost.